Hello everyone, and welcome to the Latin American webinars on physics. My name is Nicolás Bernal from the ICTP-SAIFR in São Paulo, and I will be your host today. So our speaker today is Mattia Fornasa from the GRAPPA Institute in Amsterdam, who will talk about the diffuse gamma ray background. So Mattia received his PhD from the University of Padua, right?
Yes, correct.
Yeah, so and after a couple of postdocs, so 2 appointments, one in the Instituto de Astrofísica Andalucía and then in the University of Nottingham, he moved to Amsterdam, where he's a postdoc in the GRAPPA Institute. So Mattia's talk today is titled The Anisotropies in the Diffuse Gamma Ray Background. And we are glad to have him here today as our speakers. So first, let me remind that you can be part of the discussion, writing questions and comments using Google Q&A system, and on Twitter with the hashtag LAWP, so Latin American Webinars on Physics. So Mattia, I think you can go on.
Yeah, thanks, Nicolás. I guess you can hear me, right?
Yeah.
Good. So, well, I'm very happy to take part of this series of webinars, and I think it's a very good idea, so thanks for the opportunity. And I'm also quite happy that I can talk about one of my favorite topics, which is the diffuse gamma ray background. So I think I can maybe show you the slides. Let's see. Let me put them on full screen. Tell me if there's any problem. You see them all right?
It's black, actually.
It's black. Good. Let me try again. What about now?
It's not full screen, but I mean, we'll do the.
Okay, let me try. Do you see them full screen now?
No.
No. One last try.
It's black again. I think you can do it without the full screen. It's not
Okay.
a big problem.
Okay. But now you don't see even the slides.
No, now it's completely black for me, at least.
Sorry about this.
No problem.
Can you see them now?
Yes. I think you can proceed.
Exactly. Let's go from here. So as I was saying, this is about the diffuse gamma ray background. I'm gonna mainly tell you about a project that I conducted with all of these people, and the paper is finally out. It's been published on the archive since 3 or 4 weeks. You see there the number, and it's a measurement of the anisotropy angular power spectrum of the diffuse gamma ray background. So my idea is to tell you something about the diffuse gamma ray background, then report the results of our measurement. And let's see how I go with time, but probably I will end up mentioning dark matter only towards the very end of the presentation. Even if dark matter is actually the reason why I got interested in the topic of the diffuse gamma ray background at the beginning. So let me start. This is a map of the gamma ray sky as the Gamma Ray Telescope Fermilab sees it. It actually contains all the gamma ray events observed by Fermi after 5 years of data taking, above an energy of 1 GeV. The map is in galactic coordinates, so the galactic center is at the very center. And this horizontal band that you see is the emission associated with our own galaxy, with the Milky Way. That's what I will call the galactic foreground, due to the interaction of cosmic rays with interstellar medium and the interstellar radiation fields of the Milky Way. And then all over the map, you see a lot of these very bright spots, points, these are individual point sources that Fermi detected. In the most recent version of its source catalog, what is called the 3FGL, the catalog contains almost 3,000 sources, and a huge effort has been going on in trying to identify those sources. Some of them have been identified as blazars, so this is emission produced by a supermassive black hole when it shoots its light directly towards us. Some other of these sources can be other galaxies, like the Milky Way, but of course from outside our own galaxy. Or you can have other astrophysical objects like pulsars, or what are called misaligned AGNs. The thing is that if you start from this map and start to peel away, to subtract the components that we know of, so the galactic foreground and the sources, well, you don't end up with zero. There's a residual emission that comes from approximately all over the direction of the sky in an homogeneous way. And that's what I will call the diffuse gamma ray background, this residual emission. And it's not something that should surprise you, because, I mean, at the end of the day, these sources, the one that you see here, are only those that emit with a sensitivity, with a flux, which is higher than the sensitivity of Fermi-LAT. But of course, there are other objects that emit in a fainter way, that are weaker, and that Fermi-LAT will not be able to individually detect, individually observe. Those objects will still emit light, and cumulatively, they will produce a somehow diffuse glow that will come from all the directions around us. And that's a diffuse gamma ray background, the cumulative emission of all the sources that are not bright enough to be detected individually. If I go to the following slides, you see here the energy spectrum of the diffuse gamma ray background. So this is flux on the y-axis, so number of photons per units of collective area, observation time, energy, and steradiant. So flux is a function of the energy. You should look at this, for example, at the black data points. This tells you basically the intensity of the diffuse gamma ray background as a function of the energy, and how are these points determined? Well, what you can do is build a model for the whole gamma ray emission that we saw in the previous slides in the map. So your model will have to contain a component for the galactic diffuse emission, a component for each one of the individual sources, and then you also add a template for the diffuse gamma ray background. And you leave the normalizations in front of all of these terms free to vary, and you use the model to fit the data that we saw in the map earlier. The best fit normalization of the template that you use for the diffuse gamma ray background will give you the intensity, the measured intensity of the flux. And you do that for each energy bin, and you get these points over there. Actually, there are not just one data set. You see 3 different data sets, the blue, the black, and the red one. And that's because depending on how you model the diffusion of the emission of the Milky Way, you end up with slightly different values of the diffuse gamma ray background. Overall, these systematic uncertainties can be as large as to 15–30%, depending on the energy range. And that's expressed in the plot by the yellow band. Anyway, overall, you can say that the spectrum of diffuse gamma ray background is compatible with being a power law with a slope of around 2.32, at least at lower energies. And then at around 100–200 GeV, there's an exponential cutoff that explains the higher energy part. This is also a good point to tell you that the community does not agree on a way to call this emission. So I've been referring to it as the diffuse gamma ray background, but other people call it the isotropic gamma ray background. So IGRB, that's what it's called. That's what is written in the figure. Other people call it the extragalactic gamma ray background, so EGB. I'm telling you this simply if you find yourself reading a paper where they use different names. One interesting thing is that you can actually estimate how much different classes of unresolved astrophysical sources contribute to this diffuse gamma ray emission. And we can see that in this other plot. So the black dots, the black data points, again, show the same data set as before. And then there are these 4 different colored bands. These bands, they show how much possible classes of astrophysical objects contribute or account for this diffuse gamma ray background. So you have the blazar that I was mentioning before in orange, the other galaxies in blue, misaligned AGN in green, and the possibility of having also pulsars down here. You have bands and not just one line, because estimating these contributions involves some kind of uncertainty, so you end up with a band. And how can you do this? How can you try to measure or estimate how much how specific sources contribute to the emission? Well, if you think, for example, at blazars, this is a class of sources that dominate the catalog of the object detected by Fermi. Almost 1/3 of all the sources detected by Fermi in the last catalog, in the 3FGL catalog, are blazars. And then you can build plots like this one, where you basically see the number of blazars detected above a certain flux as a function of the flux. So you start at large fluxes where you have not many objects, and then you go down, you have more and more blazars until you reach the sensitivity of your telescope. And then you can fit these points, and you see, for example, that a broken power law provides a good fit to this data. If you assume that this same behavior, this same broken power law, also extends below the threshold of your telescope, then what you can do is integrate the area below the gray line, and that will give you an estimate of how many sources will remain unresolved and how much they contribute, they emit light. Of course, this is a very good idea for blazars because you have a lot of them, but if you focus on another class of sources, like for example, star-forming galaxies, well, in that case, you only have very few sources detected by Fermi. We're talking about of the order of 10. And you cannot do population study. You cannot build plots like this one with only 10 sources. So in that case, what you can do is try to identify some relations, some correlations with the luminosities of star-forming galaxies in gamma rays with respect to the luminosity in other frequencies, in other wavelengths. So for example, in the case of star-forming galaxies, we use infrared data. And this is what you see there in this other plot. So the black data points are the few star-forming galaxies detected by Fermi, and they relate these plots related to luminosity in gamma ray with the one in infrared. You see that those points fall more or less along the same line. And at a lower frequency, the sample of resolved star-forming galaxies is much larger than in gamma rays. So you can do population studies at lower frequencies. And then you use this established relationship to translate whatever you have learned at lower frequencies to the gamma rays. And there you can estimate how much star-forming galaxies contribute to the diffuse gamma ray background. Anyway, if I go back one slide, it doesn't matter how we get to these colored bands. What you can see already from this plot is that these 3 classes of sources, so blazars, galaxies, and misaligned AGN, they seem to do a very good job in reproducing the data, and reproducing the black data points, which tells you that if you come up with any other possible emission mechanism, any other possible contribution, you know for certain that that contribution will have to be subdominant. And you can actually use these data to put some limits on that additional contribution. This is what is done, for example, in the case of dark matter. We know that dark matter halos surround and embed galaxies and groups of galaxies, and those dark matter halos can emit gamma rays when dark matter particles annihilate or decay. However, they're normally very faint sources. We haven't been able to univocally detect a dark matter-induced gamma ray flux. So all of dark matter halos emitting gamma rays will contribute somehow to the diffuse gamma ray background. But we know already from this plot that dark matter contribution will have to be small, and you can put some constraints on that precisely from this data. Good. So we already learned a lot. We know what the diffuse gamma ray background is. We know that you can estimate how much different classical sources contribute to it, and how you can use that to put constraints on other components. And this is, of course, not the end of the story. And I mean, if you think about it, until now, we've only discussed the overall average emission of the diffuse gamma ray background. But it is possible that you can learn a lot more about that if you focus on its morphology, on how much the emission changes from point to point. And one standard way of estimating that is computing what is called the angular power spectrum. This is exactly the same technique that proved to be very efficient in the case of the cosmic microwave background. What you do is you start from an emission, and you decompose that in spherical harmonics. That will give you the ALM coefficient, and the angular power spectrum, the CL, is the average of the ALM squared with the same L. So what the research program, what we would like to have, is very similar to what we discussed until now in the case of the intensity. We would like to have some data on the angular power spectrum, and then also at the same time develop a model that tells you how much different objects, different classes of objects, contribute to the angular power spectrum. In that way, you can see if, as it was happening with the intensity, you can reproduce your data on the angular power spectrum in terms of one to few classical sources. And if you manage to do that, then again, you can use your data to constrain other possible subdominant components. This is my research program, what I have in mind, what we would like to achieve. And this is also something that I will tell you in the next minutes, in the remaining part of my talk. But before entering this, I would just want to stress one point that will be important later. And this is related to what is called the Poissonian noise. So if you focus, for example, in one specific patch on the sky, like for example, this box over here, and then you receive some gamma ray emission from that. This is, for example, a fraction, a certain patch of the diffuse gamma ray emission. I told you that the diffuse gamma ray emission is due to the cumulative radiation of unresolved sources. So in principle, I'm not allowed to identify every source as a purple points because these sources are unresolved. But this is just a very naive sketch. Just bear with me in a second. I just want to make a point. What we would like to do is computing the angular power spectrum on this patch of the sky and use that observable to get some information to constrain somehow the sources producing the radiation. And you may be able to do that or not. And that depends a lot on how many sources you have in your region of observation. You may be able to do it in this case, and indeed you see that the sources are somehow clustered around a particular region. But it may also be the case that your emission is due to much fewer sources, like in this case. And of course, in this case, in the middle, there's no hope that you will learn anything about their distribution. If you compute the angular power spectrum in this case, what you will end up with is simply something that is flat in L, flat in angular multiple, or what is also called Poissonian, which is a characteristic. A Poissonian angular power spectrum is a characteristic of sources that are unclustered, that are randomly distributed in the sky. And this is a unavoidable component. You will always have a Poissonian component in your signal. And if you want to extract information on the distribution of sources, you better hope that that term, the one that relates to the morphology, to how they are distributed, it needs to be larger than the Poissonian term. Just to give you an idea, on the last plot here on the right, you see what you expect from the emission due to unresolved blazars. This is a very old estimate, but it's one of the first papers that computed these terms. I wanted to give credit to it. What they're doing is plotting the CL, the angular power spectrum, as a function of L, of multiple, and it's also being multiplied by L times L plus 1. So something that is Poissonian, is flat in L, appears here as proportional to L squared, more or less. And that's the dotted red line over here. While on the other hand, the term that actually is relating to how the sources are distributed in the sky is either the purple or the blue lines, the dashed line over there. And well, that depends on which line depends on the specific of how the blazars are modeled. But the important point that I would like to stress is that at least over here at large multiples, the Poissonian term is always larger than the one related to the correlation of sources in the sky. So down here, you will never be able to learn any information about how the source is distributed because your signal will always be dominated by the Poissonian term. And this is something that you cannot change. That's just how many sources you have in your signal. There's nothing you can do about that. So just remember this for the following slides. In the case of unresolved blazars, their angular power spectrum is dominated by the Poissonian component related to how many sources you have in the sky. And then just one last comment. When you go back to your data with your map of gamma ray events in the sky and you try to compute the angular power spectrum on that map, well, in that case, you're talking about gamma ray events detected by Fermi, by a telescope. And those events are nothing more than a huge list of gamma rays with a specific energy and a specific direction in the sky. When you plot them in a map, again, you're talking about points in a map. They will be associated to another source of Poissonian noise, just as this one. In this case, it will be related to the number of gamma ray events that you detected and not the number of sources. But that's another Poissonian term, just as this one, unavoidable. So if you want to detect any significant angular power spectrum, you better hope that that signal is larger than the Poissonian term associated to the number of events. In order to distinguish this kind of Poissonian term to the other one, the one related to the sources, they called the one related to the photons just photon noise, sorry. So you better hope that your signal is larger than the photon noise. But one thing that you can do to reduce your photon noise in this case is simply leaving your telescope, letting your telescope on for more and more time. You will gather and collect more data, increase the number of events, and reducing the photon counts. Okay, so after this introduction, let me tell you about our measurement. This is not the first measurement of the angular power spectrum. The original and the first one is dated 2012, and it was produced using 22 months of Fermilab data. We now are using almost 4 times the statistics, 81 months. We also extending the energy range considered, going from the energy window between 1 and 50 GeV to 3 orders of magnitude, covering the range between half a GeV to half a TeV. And you see the data that we used in one specific energy beam in the map over there. We computed the angular power spectrum on the masked sky. So we mask all the regions in the sky where we know the diffuse gamma ray background is just a subdominant component. So we mask the galactic plane and all the sources. We actually considered 2 different masks. In one case, we mask all the sources in the latest version of the Fermi catalog of detected sources, so all the masks in the 3 of the sources in the 3FGL. And then independently, we also consider another mask that only covers the sources present in the older version of the catalog, the 2FGL. And in everything that you will see in the next slide, the results will be presented for both choices of the mask. What you see here in this slide is actually our angular power spectrum estimator. So this part here is what comes out from the decomposition in spherical harmonics. And to that, we subtract the photon noise that I was telling you about. That is this unavoidable component related to how many gamma ray events your telescope has detected. So a significant signal means something that is larger than Cn. So we are looking for excesses over Cn when this difference is significantly different than 0, so that's our detected signal. And then we also have to correct for the effect of the point spread function of the telescope, so the angular resolution. And we do that by dividing for this function called window beam function, WL. You see some example of the WLs in this plot over there. So that's window beam function as a function of angular multiple L. Different colors stands for different reference energy. And you see that the effect of having a finite angular resolution is that the signal WL is damped, decreases at large multiples. If you go at very low energies, like in the case of the black curves, this damping already starts to occur at a multiple of around 100, 200. And then, yes, I should tell you also something about these indexes over there, I and J. They label the energy beams, because not only we compute the angular power spectrum inside each of the 13 energy beams that we consider, so that would be when I is equal to J, but for the first time, we also compute the cross correlation between the emission between different energy beams. So that would be the case when I is different from J. So from now on, whenever I'm plotting CL, whenever you will see the CL, it's always this angular power spectrum estimator. You see some two examples in this slide. So that's again, CL is a function of L. On the left, for one energy beam at low energies, and on the right, for one energy beam at higher energies. There are two different data sets, a blue and a red one. The red one is for the mask covering sources in the 3FGL, and the blue one when we consider the mask around the sources in the 2FGL. The blue data sets are systematically higher than the red ones, and that's because in that case, you're still sensitive to the anisotropy produced by those sources that will be detected in the 3FGL, but that are still unmasked in the case of the 2FGL. And both datasets are also systematically higher, larger than 0, at least in the case in the left panel, which means a detection, a significant detection of significant power. And you should also note those two vertical lines, dashed gray lines, that defines our multiple region. So we neglect anything below L of 49 and above L of 706, and that's because we want to we want to get rid of any possible contamination due to the galactic foreground, and also to the multiple region or multiple range where the correction due to the PSF becomes too extreme. So we only focus in this central region. We take these remaining 10 data points and fit them with a flat line, with a Poissonian angular power spectrum. And we find that in all the 13 energy beams of the autocorrelation, and also in all the possible independent combination of energy beams, a Poissonian angular power spectrum, a flat line, is always a good description to the data. And you can actually see that in these plots. The horizontal solid red line is the best fit Poissonian angular power spectrum to the red circles, and the dashed blue line is the best fit Poissonian angular power spectrum to the blue squares. And the fact that these data are well described, well fitted by a Poissonian angular power spectrum, by a flat line, is a good news for me, because now I don't have to show you all of these plots for all the different energy beams. I can just give you one number, which is the intensity, where to put this horizontal line. So that's what I'm doing in the following slides. What you see here is the best fit Poissonian angular power spectrum for the autocorrelation in the 13 energy beams as a function of energy, for the mask around the 3FGL in red and the mask around the 2FGL sources in blue. This is also what is called the anisotropy energy spectrum. And, well, first of all, it gives you an idea of the significance of our detection. So points around here, they're different from 0, so signal, with a significance of around 7 and 8 sigma. And you go below 3 sigma only for these last 4 red points, and these two over there. So this is a the significance of the detection is much larger than the original 2012 measurement. And also this quantity, the anisotropy energy spectrum, turned out to be very, very informative to infer, to constrain the components of the anisotropy power, of the anisotropies angular power spectrum. And that's because you should remember that at the end of the day, this power, the CL, is nothing more than the average of the ALM squared, which comes from the composition of the original intensity map. So if your intensity map depends on energy, as it does, we know it does, the ALM coefficient will also depend on energy. And the angular power spectrum will inherit the same dependence on energy, but squared, of course. You can actually factor out the dependence on the energy in this way. So the best fit Poissonian angular power spectrum in the combination ij of energy beams can be written as the intensity in the two energy beams I and beam j, times an energy independent component. And if your signal is due to only one population of resources, well, that's the end of the story. This part, on the left-hand side, you measure. This is what we are showing here. And from this, you can directly read, you can directly infer how your sources emit in energy. In the case of more than one population of sources, then things become a little bit more complicated. The contribution of the two populations sum linearly. So you have the case of population A plus the case of population B. And inside the population of sources, you can do the same decomposition as we were doing before. But in this case, you may think of a scenario in which you have, for example, population A dominating your signal at low energies with a very soft, so steep energy dependence. And then at some point, possibly population B will start to kick in with a harder energy spectrum, so that the overall energy dependence of the signal will not be flat, will have some feature or breaks. It is just to tell you that indeed any feature that you can detect in the way the CP depends on energy can be considered as an indication of multiple populational sources contributed to your signal. And indeed, we were very happy when we saw for the first time this plot, where it does seem that the anisotropy energy spectrum is not just flat, just a boring power law. We can be even more precise if we take into account also the cross correlation. So the cross correlation is, I could have shown the same plots like this one for the cross correlation as a function of the energy, but I think a better way of understanding this is by considering what is called the cross correlation coefficient, the Rij, which is simply the cross correlation in the combination of energy beams Ij divided by the autocorrelation in the two energy beams separately. So if you keep track of the energy dependence as we were doing before, so let's say we have the same expression as before, you put this at the numerator. In the case of only one population of sources, well, that's easy. You just rewrite the numerator in this way. And in the case of the denominator, you have I equal to j, and you can easily understand by yourself that the energy dependence exactly cancels from numerator and denominator. So the cross-correlation coefficient R will be identically equal to 1. That's the case for one population of sources. If you have more than one population of sources contributing to your signal, then the components sum, and this cancellation from numerator to denominator does not happen anymore, which means that if you have some coefficients different than 1, that's again a signal of more than one source classes contributing to your signal. And we can see that in those two plots in the slide. So on the left, it's the case where you mask the sources in the 2FGL, and in the right, where you mask the sources in the 3FGL, and plotting the cross-correlation coefficient of all the 13 energy beams against the other energy beams. So these plots are, by construction, symmetric along the diagonal, and the diagonal entries are identically equal to 1. But you see clearly by eye that there's a region around here when you're cross-correlating low energy beams with low energy beams, where the coefficients are around 1. But then another region down there when you're cross-correlating low energy beams with high energy beams, where the coefficients are around 0. And that more or less falls in the same scenario that I was depicting before, right? A population of resources contributed at low energy and a different one contributing at high energies. So this is for 2FGL. In the case of 3FGL, you kind of see the same structure. You have to maybe squint around a little bit. Of course, these data points are affected by a larger error bar, so it's difficult to see it. But we can even be more quantitative. And what we did was try to fit this data, both the autocorrelation and the cross-correlation, by some phenomenological models where we assume one or more source classes, and also we assume that those source classes emit either as power laws in energies or broken power laws. So the best fit case in the case of only one population of sources is plotted in the panel on the left by means of the pink and blue line. And in this case, whether it's a broken power law or a power law, those fit are not very good ones. You see that both cases underproduce the very two energy beams. If you go to two population sources, then you need to look at the plot on the right. Here we have the case where there are two power laws in yellow, one broken power law and one power law in green, but the best description to the data is provided by two broken power laws. That's the thick black line that is plotted, that is shown in both panels, both on the right and the left. And in this case, the thick black line, the two population resources are shown independently by the dashed blue lines. So again, as I was saying before, you have one class dominating the data around 1 GeV or below, and then the second one, with a much flatter, harder spectrum, reproducing your data at higher energies. And in the following slide, I'm giving you the details of the best fit model parameters of the two population sources. We can actually, by performing a likelihood ratio test, exclude with a 95% confidence level the interpretation in terms of only one population of sources with respect to the one with two classes. And that's the first time that we can do that. So this concludes more or less my presentation of the measurement. Of course, this is a very naive exercise, what we did with the phenomenological description of possible source classes contributed to your signal. What one should do and could do is devising or build up a model where you have physically motivated, physical sources, and then use these data to constrain the model of your first principle physically motivated astrophysical sources like blazars or star-forming galaxies. We're not doing that in the papers. There's still room for some work. In the paper, the thing that we do is instead using these data to put constraints, to put upper limit on a possible dark matter components to the anisotropy signal. And I will be very, very brief on this, just telling you that, well, if you want to compare this data with the possible dark matter-induced angular power spectrum, then of course you have to estimate how the dark matter signal looks like. You can do that including components that come from extragalactic dark matter halos objects, like you see in the top panels, and the galaxy itself in the bottom panel. You have both the case of annihilation and decay. You compute the angular power spectrum on these maps. That's what you find. So again, CL in one specific energy beam as a function of L. You see different color bands because we consider different components to the signal independently. And we also take very good care in estimating how much each component is affected by some systematic uncertainties related to how we model the dark matter distribution. And then you have to compare this prediction to the data, which in this case is represented by this black line. And then, of course, you can use this comparison to put some exclusion limits on the dark matter signal. The easiest thing to do would be requiring that there's no energy beam in which the dark matter signal is larger than the detected signal, than the data. And that will give you some exclusion limits that can be translated into upper limits on the annihilation cross-section or the dark matter particle as a function of mass. So everything above this colored line is excluded. And we have 3 lines, the blue, the black, and the red ones, because we consider these 3 cases as 3 possible benchmarks related to how we model the distribution of dark matter in the sky. Alternatively, in the case of decaying dark matter, then what you have are lower limits, excluding everything below this colored line. And you should compare this exclusion limit with what is available in the literature. So if I focus on annihilation, our exclusion limit should be compared to the thermal value of the cross-section, so dashed gray line here, or to the exclusion limit that you can have from the observation of those spheroidal, which is those dashed gray line. And unfortunately, we are something like a factor of 20 above these other upper limits. Or then also you can do something more constraining, for example, devising this 2-component fit to the data, where you model at the same time a possible dark matter signal plus a Poissonian component, which is supposed to describe, any other astrophysical contribution. And in this case, the upper limit comes by requiring that adding the dark matter component do not spoil the Poissonian interpretation of data too much. And again, everything above this 3 colored line or below this band is excluded, thanks to these more aggressive constraining methods. So I guess this is it. I just want to briefly mention that at this moment, we've only considered, the interpretation that comes, the information that comes from diffuse gamma ray background alone. But you can gain even more insight if you cross-correlate your diffuse gamma ray background with other observables, like, for example, catalogs of resolved galaxies, or even the information related to the large-scale structure that you can extract from gravitational lensing, either from galaxy-galaxy lensing or CMB lensing. And we have measurements, in some cases even detection, for these cross-correlation terms, and they are complementary to what I told you about in this presentation. So yeah, I think that's only my conclusion slides. I just want to say again that we have a new measurement of the angular power spectrum of anisotropies. For the first time, there's evidence that the signal comes from multiple components, and with this measurement, with this new data, you can gain more insight on astrophysical sources, and you can put constraints on other contribution, like, for example, dark matter induced gamma rays, and the exclusion limit that you get are competitive with what you get from simply considering the overall intensity of the diffuse gamma ray background, forgetting about any anisotropy. So yeah, that's it.
Thank you, Mattia, very much. Hello, yeah, you can hear me, I think. So yes, thank you, Mattia, for this super interesting seminar. Now we should pass to the round of questions. So please remember that you can ask questions to Mattia via the Google Q&A and the webinar webpage, and via Twitter as well, with the hashtag LAWOP. So first, our question here from the audience. Roberto, I think that you have one.
Yeah, I have.
Please go ahead.
Nice. Okay, I have a question for Mattia. But first of all, very nice, the webinar.
Thanks.
And I want to ask you, because you presented all these constraints in terms of the annihilation or decay spectrum into BB bar channels. How it changed? How is the dependence with respect with other channels? If it is less, I mean, do you require to have a soft spectra in order to make this cross correlation between different beings in energy, or a sharp one also would make the job?
So we checked, and we considered 3 different possible channels: BB bars, taus, and years. And in none of those cases we identify features in the data that suggest a possible diagnosis. So in all of those 3 cases, you still only can put constraints. And the actual constraints, both for annihilation and decay, you can find them in the paper. They are the relative plots.
Okay, thank you. So in that sense, the BB bar is the most standard. I mean, the most nicer, I guess, no? Because I didn't check I'm gonna check the paper, of course, but it's like
what do you mean by nicer? You mean more constraining?
Yeah, more constraining. Yeah.
I think so. Yeah.
Okay, I have one question, but maybe other people can ask me what.
So I also have a question, Mattia.
Please.
So I was just wondering, why did you use the 2 masks? So the 3 catalog, the 3 FGL and the 2 GL?
Right.
So is that you're not trusting the 3 FGL catalog?
No. You really should consider them as 2 independent measurements. And indeed, since you know which are the sources that you are masking in, the new sources that you are masking in the 3 FGL sources, having 2 different masks help a lot in seeing the effect of those sources in the way the CP depends on the energy. So you can relate how the 2 different data sets change to the effect of the sources that you have masked. For example, if you imagine that you're going from 2 FGL to 3 FGL, you're only masking sources that contribute, I don't know, below 2 GeV, then you should clearly see that effect in the way the CP depends on the energy. You should only see differences below 2 GeV, including different cuts in sensitivity, in flux, help you understand what's the effect of the sources you're masking in the signal.
I see, thanks.
I have a question.
Yes.
Yes, when you show the CL, the measurement, I think it was on page 9. So, and you show the values of multiple in which you fit your data. So from 40 to, I don't remember,
700.
Yeah. So how do you choose them?
Yeah. So at low energies, we introduced lot multiples. We introduced the cut to get rid of the possible contamination for the galactic foreground. Can I go back to the slides? Let me share again the screen, if I manage. Do you see it?
Yes.
So yes, look at this map over here. We're masking the diffuse gamma, the diffuse foreground, but even outside the mask, there's still some possible contamination due to the galactic foreground. And however, these are large scale feature that we only contribute at low L. So the cut at low L is introduced to get rid of these features. And we check different cuts in L and determine that the value of 49 is the lowest we can get to be sure that we are indeed cutting everything from the galactic foreground. At higher L's, so here above 708, that's where the error bar starts to blow up because of the corrections due to the PSF. And that's a value that, I mean, this doesn't matter much because in any case, producing a fit to these points with a huge error bars wouldn't change much your results of the fit. By the way, since, as I showed here, the effect of the PSF, the window beam function, is important specifically, in particular at low energies, this effect, the blowing up of the error bars, shows up particularly at low energy. So in this panel and not in this one. We could have increased the multiple range at higher energies to higher multiples. So going up to, I don't know, a couple of thousand in this case, only at higher energies. But we decided to work with a constant multiple range. So we decided to go for, 706.
Yes, okay. And maybe I can ask a second thing. When you have the final results, the CL is a function of the energy.
Okay.
For the free FGL case, you have a deep around 10 GeV, right?
Yeah.
So do you have an understanding of that, or is just you think it's just statistical effect, fluctuations?
We think it's just a statistical fluctuation. And indeed, so you mean
Yeah,
this?
exactly. Yeah, the blue ones are actually there, but the red ones go down.
The other ones are they have larger arrow bars. And we do think this is just a statistical fluctuation. Indeed, if we change some of the details of the analysis, like for example, the fact that these data points are obtained only considering events that convert in the front head of the telescope, but if we also include the one in the back, then these two data points go a little bit higher. So this feature, this dip, is not stable by considering different selection in the data processing. So we do think it's just a statistical fluctuation.
Okay.
We've also played a bit with past data. So that would be the even more recent reanalysis of all the events detected by Fermi. And even in that case, those 2 points disappear. Well, disappear. They go higher. Sorry.
Yes. Yeah. Okay.
Okay, I can see a question from Aaron Vincent. So he's asking whether there's here any insight with respect to the Lee et al. Paper about unresolved point sources.
You mean the one on the galactic center? That would be a different target, right?
I don't know.
So if I have the correct paper in mind, they use a different method related to the one-point photon count distribution to analyze the region around the galactic center, while we are focusing on the overall distribution of the diffuse gamma background. It would be interesting to do the same analysis that they do, also on larger scale of diffuse gamma background.
Well, if I can I add something?
Please.
Yeah, actually, this has been done.
Okay.
High latitude. This is the Zekring et al. Paper. Actually, there are 2 papers where the same kind of analysis is done not at the galactic center, but for high latitudes. So it's basically constructing the log n log s distribution for the unresolved part of the sky, which is at high latitude. So actually, it's done.
Okay, thanks, Nicolás.
Very good. Are there more questions? I don't see. I see a question from Sergio Palomares. So he's asking, will you expect a shoulder from cascade of high energy photons even with a single power law? Or in different words, is the cascading process taken into account in your results?
No, it's not taken into account because our interpretation is really just a phenomenological, naive level 0 first thing that you try. But cascades should be included, absolutely. And in principle, they can produce feature in your energy spectrum, especially at lower energies, since what is driving our fit are the very, very 1 or 2 points below 1 GeV. Then of course, the low energy part of the spectrum should be correctly modeled. So that's a very good point. We're not taking into account that.
I see. Thanks. So there are more questions from the audience, maybe the last one?
Yeah, I have a couple more. Mattia, in your slide number 3, there is the star-forming galaxy spectrum. Why it stopped at 10 to the 5 MeV? There is a reason, or do you expect like a cutoff, natural cutoff or something like that?
Let me go back, sorry. This one, you mean?
Yeah.
Yeah, so I must confess that there's no reason. We just, since this comes from taking the prediction from a paper, the prediction from that paper was just stopping here. So we couldn't plot anything above that without having to reproduce their results. So there's no physical reason. It should go down following the same behavior.
Okay, it's like expected like a a damping factor.
Well, I mean, it's a power law, and then at some point there's the damping due to the EBR attenuation, like with every astrophysical source.
Yeah.
Sources.
Okay. So yeah, a little bit with this, the same idea. I mean, when you make the analysis with two broken power law, it's not could be equivalent to a power law with a exponential cutoff, like is the phenomenological assumption for some type of dark matter spectrum.
So you mean if the break that we see at high energy can be due to the EBR absorption?
Yeah. Oh, yeah. Any process that produce a exponential cutoff, like a damping at the not a broken like a sharp edge, but more soft damping.
Absolutely. And I mean at the end, I mean these points at higher energies are the one with the largest error, so it would be easier to fit something that goes down in any way, right?
Yeah, it's true. and the other, because since all the questions are more or less correlated, the point that then when you compare for instance the constraint from the dwarf galaxies and this method, what is the point that is restricting more why you cannot go with stronger constraints? It's just a lack of statistic, or is the apparatus itself the APS of Fermi?
Okay.
That doesn't allow you to do better than the dwarf, for instance.
Yeah. I think what is dominating these results is the measurement that you have. You would like to have smaller error bars on the CP, on the detected anisotropic angular power spectrum, so that you can be sensitive to smaller deviation compared to the overall Poissonian description. If you can reduce, if you can reduce these error bars, then you will be able to put more stringent constraint. And that comes at the end of the day is relating to statistics and the possibility of maybe extending the multiple range in order to have a longer lever arm when you do the fit. Something like that. There's already been a huge improvement, a huge step forward with respect to the original measurement of 2012. In that case, we had detection of power of angular power spectrum of the order of 5 sigma, only around 1 GeV. And now we extended it to lower energies, and the significance increased thanks to the improvement since 2012. Going to PAS8 is expecting to again be another important step forward. So we should redo the analysis of PAS8 as soon as possible.
Yeah, and more or less there is a time window for that, maybe next year, 2 years, 2 more years to.
I know that there's work, but I'm now involved in that, so I can give you a time scale.
Mm-hmm. Okay, thanks. I don't know if the others has questions.
So I don't see more questions. So yeah, so let's thank Mattia again and all our viewers.
It's a pleasure.
Yes, thanks a lot. And we'll meet in 2 weeks for the next Latin American webinar on physics. So thanks a lot, man.
Bye-bye.
Ciao.
Bye-bye.